Marcelo, habla un poquito, porque estoy en el YouTube, yo estoy viendo otra cosa.
Sí, yo no veo también nuestra transmisión.
Ahí sí, faltaba que hablaran. Tú que hables más Castillo. Mira finalizar.
Hola,
No, está abierto.
hola, aquellos que ya están llegando. We are testing, we'll start in a few minutes. Hello, we are testing, we'll be live with Professor Economy in a few minutes.
Marcelo, are you there?
I'm ready to start if you want.
Okay. I give some little words in Spanish if you because not all the people speak English. They are going to use the translator of the YouTube.
Sure.
I think we can begin, right? We are online now. Mm-hmm.
Yeah, yes, maybe you can stop sharing for a moment, Giannis.
Okay.
Ok,
Vamos a empezar.
vamos a empezar.
Ok. Bueno, primeramente, yo soy Christian Scherer y me gustaría presentar aquí a nuestro chairman, Marcelo Castier, y al profesor Ioannis, quien le va a presentar el profesor Marcelo Castier. Y estoy muy contento de que todos ustedes estén presentes ahora y estén escuchando esta charla, que es el primero de nuestro seminario en computación científica y matemática aplicada. Marcelo, todo tuyo. Muchísimas gracias y estamos con muchas ganas de tener colaboraciones, alumnos y poder seguir avanzando en lo que sea la computación científica y la matemática aplicada. Buen día a todos.
Buen día, bom dia. Hello, everyone. Welcome. Thank you, Christian, for the introduction and for the welcome. I share the welcome Christian has given to all of you to our seminar series on computer science and applied mathematics of the Polytechnic University of the National University of Asunción. It is a great pleasure to start this series, to launch this series with a very distinguished speaker, Professor Ioannis Economou. Ioannis graduated in chemical engineering from the National University of Athens in Greece, and then obtained his PhD also in chemical engineering from Johns Hopkins University. During his illustrious career, he has worked in a number of countries: the Netherlands, the US, the UK, Denmark, United Arab Emirates, and Qatar. On several positions, he spent a considerable number of years at Democritus, a research center in Greece, and he is currently at Texas A&M at Qatar, where he is a professor of chemical engineering and senior associate dean. So it's a great pleasure to have you here, Ioannis. And before I give the word to him, let me also mention two important things. He is the founder of the Working Party on Thermodynamics of the European Federation of Chemical Engineers, which is like the focus group on thermodynamics in Europe. And he is the editor of Fluid Phase Equilibria, which is possibly the most important journal in the field. His research interests are very broad: development of models for the calculation of thermodynamic properties, the development of algorithms, but today he will focus on computational applications, the molecular simulations and its applications. Again, before I give the floor to you, Ioannis, let me comment that we are making this broadcast through YouTube, and you can interact with us by sending your comments or questions on the chat on YouTube, and I will pass these questions to Ioannis at the end of, after his presentation, so that we can have room for some discussion. Without any further ado, Ioannis, the floor is yours. Welcome.
Thank you very much. Thank you very much, Marcelo. Thank you very much, Christian, for giving me the opportunity to be here with you today. It's a great pleasure and honor to give this seminar, which is, I guess, the inaugural seminar for this new activity that the Universitat Nacional de Asunción is putting together. As Professor Castier mentioned, I have worked in different places. I have never been to Paraguay, and I have never been to South America in general. So this may be a start for collaboration in the future. As Professor Castier mentioned, my area of expertise is mostly on molecular simulation and molecular thermodynamics. So today I have decided to talk in general about computational molecular engineering and to provide a few examples on how it can be used in order to design chemical processes and advanced materials. And I am a chemical engineer, so all these kind of techniques or these advanced computational tools, they're very important in chemical engineering in many different ways. Before I get into my actual technical talk, I would like to give an overview of where I am at the moment. So I am in Qatar, and Texas A&M University is based in Qatar Foundation, which is an organization like the Ministry of Education for this country. It has been founded in 1995, so we're getting close to 30 years. And essentially, the vision of the institution here is to provide world-class education that starts from the kindergarten, the preschool, all the way to the graduate degrees, graduate programs like master and PhD. And they do this through a number of collaborative activities, the most important of which is the presence of a number of foreign universities. You can see here a lot of acronyms. Christian, can you see my pointer when I point here, please?
Yes.
Thank you very much. So Qatar Foundation started in 1998 by inviting the so-called Virginia Commonwealth University in Qatar. Then WCMQ is Weill Cornell Medical University of Qatar. This is with pink is us, Texas A&M University, Carnegie Mellon, Georgetown, Northwestern, and so on. All these are different universities that came to Qatar with a college. So we are the College of Engineering. Carnegie Mellon, which is next to us, is a College of Business and Computer Science. Weill Cornell is Medicine. Georgetown is Political Science and Foreign Service. Virginia Commonwealth is Fine Arts. Northwestern is Liberal Arts. So essentially, this is a very interesting experiment where several universities come together. And then you can see after 2005 and 2007, a number of different acronyms. These are mostly colleges of that HBKU, the Hamad bin Khalifa University. So essentially, we're on the same physical campus, on the same big campus, a number of different universities. You can see here the logos. So far, we have educated more than 6,000 students, and we have at the moment around 3,000 students. And at the moment, we are the largest of all 6 foreign universities, who have approximately 700 students, around 72, 73 faculty professors. We have around 80 postdocs. So it's a fast-growing campus. The mother campus is in Qatar, and we are a branch campus. Sorry, the mother campus is in Texas, in College Station, Texas, and we're a branch campus in Qatar. So this is essentially who we are. And before I would like to mention that we're a very international campus. We have faculty and students from all over the world. Until some years ago, Professor Castier and I, we were colleagues. Our offices were next to each other. We have also faculty coming from Asia, from America, from Europe, and so on. As I said, today I'm going to talk about computational molecular engineering. And I would just like to give you or remind you of the fact that we have amazing amount of computing power. You can see here, this is a very famous plot. You have seen it in many different ways, where you have the computing power on the left on the logarithmic scale versus time for the last approximately 30 years. And you can see that this varies linearly. So essentially, we have an exponential growth of the computing power. This is the well-known Moore's law. Moore was one of the inventors of Intel. He died 2 months ago at the age of 90-something. And Moore predicted in the 70s that the computing power will double every 18 months, and this keeps going. And I don't know if you can see here, but essentially the supercomputing power in a Cray supercomputer in 1985 is equivalent to Apple iPhone 4. That was the top phone in 12 years ago. So you could do simulations in a Cray 1995, and the same computing power was available in iPhone 4. Now we're at iPhone 11 or 12. So you can imagine the amount of computing power available. And for those of you that may be electrical engineers or computer engineers, this is how the fastest supercomputer looked like 70 years ago, the IBM 730, and this is one of the fastest supercomputers today, the Summit supercomputer. So we have a lot of power, a lot of computing power. But the thing is, we have to use this computing power wisely. And the way that you do this, you can do it in many different ways. I come from the chemical engineering background, material science, molecular engineering. So essentially what we try to do is we try to understand how the soft matter behaves at the molecular level and predict properties and design processes. So you can do this in a hierarchical way, and I have taken this from Professor Theodorou at the Technical University of Athens, where you have from the chemical constitution, you do quantum mechanical calculations, density functional theory, and so on. And through this, you are able to develop the way molecules interact, how molecules they put in place in space. So you design, you are able to calculate molecular conformations, And this gives you the opportunity to perform what is called molecular simulations. Molecular simulations is taking, for example, Newton's equation of motions at the molecular level. So you can do molecular dynamics, you can do Monte Carlo simulations, which is a stochastic way to calculate the Newton's equation. You can do transition state theory and so on. So through this, you can understand how molecules are organized, how molecules move, and people can develop mechanisms to understand the macroscopic behavior. And before you go to the macroscopic behavior, you can do a higher level of calculations, which is called mesoscopic simulations or coarse grain simulations. And again, we have different kinds of techniques. We have kinetic Monte Carlo, dynamic density functional theory, dissipative particle dynamics, and so on and so forth. And then as you go to higher level, this is when the engineering approach comes in, where you may have external processing conditions. For example, you may have a polymer, you may have a hydrocarbon fluid, and so on. So through this, you can do now calculations at a much higher level, where you can apply thermodynamics principles, transfer phenomena, reaction engineering, chemical kinetics, and so on. So this is a nice way on how you can use this tremendous computational power in order to predict the properties of end-use materials and design processes. So in this way, we can improve, we can optimize processes, and we can design and develop new materials. Of course, I would like to point out that as you move along from at different levels of calculations, always you have to check or you have to validate your calculations against experimental data. This may be, for example, NMR data, neutron scattering, light scattering. It can be macroscopic measurements, for example. You can do different kinds of calorimetric measurements, and so on and so forth. Now, again, talking about multi-scale modeling and process design, I have here elucidated a little bit some techniques that we use in my group on a time length scale. And personally, I do not claim to be an expert in all this. When I was a PhD student 30 years ago, chemical engineers used to do work in this area here, in chemical thermodynamics, in continuum fluid dynamics, and so on. Professor Castier, he's a world-known expert on developing macroscopic thermodynamic models. That my PhD was also in this area 30 years ago. But what has happened over this period of time is that chemical engineers and materials engineers, they have started looking at these sub-molecular and molecular levels, okay? What you achieve down here is you can develop understandings on how the fluids and materials behave at the molecular level. And again, all these pictures are schematic representations of projects that we have worked in my group before. So this is a cation from an ionic liquid. Over here, I have a water octanol mixture, which is very important for different kinds of applications. This you may think as a multi-arm polymer. You can think of this as a polymer brush. Depending on the functionality and the length of these arms, the polymer behaves differently in terms of viscosity and many other properties. So going this way here, going downwards, we can develop an understanding of the fluids of the materials. And then if we go upward, we can improve the design in terms of processes, optimization, and so on. So my group in general works on different areas around this red scheme that I show you here. The challenge today, especially for those of you that may be young, PhD students, master students, postdocs, because we have all this computing power, the challenge is to develop techniques at different levels and then communicate the information from one level to the other. So when I have, for example, a project that involves quantum mechanics, the question is, what kind of information do we need from quantum mechanics calculation in order to develop a force field that will allow us to do molecular simulation calculations? And then when I collaborate on a project, for example, with Professor Castier or other colleagues, what kind of information we get from molecules in order to develop a more predictive and a more accurate equation of state. And then, of course, when you go from here to further up, colleagues who work on process design, again, they get information from chemical thermodynamics, like primary thermodynamic properties, densities, for example, phase equilibria, or secondary properties, derivative properties, like heat capacities, and so on and so forth. So after this general introduction, I would like to talk about two projects that my group has been involved over the last, I would say, almost a decade. So I will give you a little bit of a history and a little bit of updated information on two projects. And and again, because I promised that what we do has to do with practical applications, I have chosen to talk about two projects with industrial involvement. The first one has to do with the Fischer-Tropsch synthesis for natural gas transformation into clean fuels. This is a project that Fischer-Tropsch is a process that has been around for 100 years, but it has gained renewed interest for the last 15, 20 years from companies like Shell, with whom we collaborate, but also many other oil companies. One of the most well-known processes, the so-called gas to liquid. Okay, gas to liquid, essentially, you take natural gas, which, of course, as we all know, is mostly methane, through a catalytic process that allows you to produce heavier hydrocarbons. So this is my general chemical reaction. And through this reaction, you can produce hydrocarbons. And here can be anything between 8 and 100. As I said, this is a catalytic process. We have different carriers, alumina, silica, titania, and so on. And this is a relatively high temperature process between 200 and 240 degrees C, and the catalyst typically is cobalt. And although this has been on for a couple of decades now, there is always a need for improvement and optimization. And I have here a picture actually of the largest G12 plant today, which is around 70 kilometers north of Doha, where I'm located. It's the so-called Shell's Pearl catalytic process. This is by far the largest G12 plant in the world, and it essentially operates something like 140,000 barrels of oil equivalent per day. So, as I said, this is a catalytic reaction, and there are a number of challenges. One of the challenges has to do with the fact that this reaction produces a lot of water. So if you have catalytic process with a lot of water, you have a number of problems. And this has to do mainly with the catalyst deactivation and the sintering. And as a result, your catalyst lifetime is reduced and the operational cost increases. Now, when you try to find out what happens at this level, at the nanoscale level, experimental investigations are very difficult and very rare. So molecular simulation is one of the techniques that that provides the means to understand what is really happening in the reactor. And of course, one of the immediate things is that, excuse me, let me go back. You can see here that you may have, this is a side reaction, but essentially you have, what do you have? You have hydrocarbon with water. And we all know from our very basic thermodynamics, even at high school, that oil and water do not mix. So you have two phases. And the question is, how does the confinement, the catalytic confinement, affects the phase equilibria? The other thing is that based on some evidence that we had from our industrial partner, in this case was Shell, the process results in some what they call oxygenated products. For example, dodecanol. So an additional question is, how does dodecanol affect the phase behavior of the system? And the last question that we wanted to provide a solution, provide an understanding, is the role of the catalyst nanoparticle. In this case, it's cobalt. So let me show you the very first set of calculations that was done more than 10 years ago. And this has to do with the diffusion coefficient of various gases. Again, the catalytic reaction involves hydrogen, carbon monoxide, and water. And this is the diffusion coefficient of these gases in various alkanes that are produced during the reaction. And you can see here that all three gases, the diffusion coefficient at two different temperatures, left and right, is at the low and the high temperature end. Qualitatively, there's not much difference, The important thing I would like to mention is that as the hydrocarbon size increases, the diffusion coefficient goes down. And the reason for this is because as the hydrocarbon becomes heavier, there is less free volume in the wax, so the diffusivity becomes more difficult. Now, when you do this kind of calculations, and this is based on molecular dynamic simulations, always you try to compare with experimental data. Back then, we had very few data. The data are with open points for the case of carbon monoxide, open points for the case of hydrogen, nothing for water. And you can see that the agreement between experiments, limited experiment and simulation was very good. But experimental data were only up to C28. So when we saw this, we were very happy that we had good agreement, but the question is, what happens with heavier hydrocarbons? And at that point, it was maybe 10 years ago, we started collaborating with one of the top experimental groups in Europe, in the University of Erlangen. And in Erlangen, they built this high-pressure cell, and they used dynamic light scattering. This is exactly the cell that we built for this project. And they used dynamic light scattering in order to measure the diffusion coefficient of these gases in heavy hydrocarbons. And we generated lots of data. This is the group of Professor Andreas Froba in Erlangen. We had several joint publications, and you can see here, I'm just showing you only just a few comparisons. On the left is C12, and on the right is C28. And essentially, I show these two hydrocarbons because these are more or less the two extremes in the product of hydrocarbons produced out of this process. And again, the experimental data are the open points, and the simulation is the close point. And let me point at this point that whoever is doing theory or simulations, always you try to do simulations for well-defined systems and to compare with experimental data in the literature. Here it was the other way around. We had the simulation, and Froba and co-workers went and measured data. And the agreement was excellent. So this is the case where you think, I mean, for me, as the project leader, how close am I to experimental data? Am I very far away? But again, the experiments prove that we were in very good agreement. So at this point, we moved forward. And moving forward means that we wanted to go to the development of a more coarse-grained level. Let me say that these kind of simulations are not cheap and they are not fast. Back then, 10 years ago, we needed maybe, we could use in a single processor a few nanoseconds of simulations. And when the hydrocarbon is heavy, we need several nanoseconds in order to get a good data point. So each one of these data points that I showed you takes more than a day. So one way to speed up calculations is by relying to what we call coarse-grained models. And one way to do coarse-grained modeling is this Martini force field. I forgot to mention that my simulations so far were based on atomistic representation. So we take into account all the centers, all the carbons and the hydrogen. On the Martini force field, there is the so-called 4-to-1 representation. So 4 heavy atoms mapped to 1 bit. And by doing this, you speed up the calculations tremendously. I do not have time to go through all the details, but one way to check your agreement of the force field is to look at various thermodynamic properties. So for example, you can see here, we have data for pure hydrocarbon, C12 and C28, and the binary mixture with a 30% C12 in the mixture. On the left, I have liquid densities. On the center, I have the vapor-liquid surface tension, and on the right, I have viscosity. These are 3 very important physical properties, very different: thermodynamic, transport, and two-phase behavior. And you can see here the 3 different force fields that we use in this work. The TRAPPE force field is the transferable potential for phase equilibria. This is a united atom force field developed by Ilya Shipman at the University of Minnesota. The OPLS, this is the all-atom representation of the hydrocarbon. And then on the right is the Martini, my full coarse-grained model. So these are 3 different levels of representation. And of course, there is some variation in the predictions, but overall, the agreement is very good, which means that we get confidence that we can move on and do simulations now at a more coarse-grained level. So The additional complexity in the system had to do with the fact that we wanted to represent a full wax. A full wax means the full mixture that is produced from the gas to liquid process. And on the left, this is what we get from our partner, from Shell, which they call it X12, essentially anything to liquids. This is a heavy paraffin, and you can see this broad distribution. So essentially, you produce hydrocarbons that have a very broad distribution. And again, we built this in our simulation box. I would not go into details. And we took this and we put it into the nano confinement. So essentially now I go from the bulk to the nano confined fluid. You can see some representation. On the left, I have the titanium dioxide, and on the right, I have silica carbide. These two different catalytic supports. Titanium dioxide is much more hydrophilic, silica carbide is much more hydrophobic. And over here, you can see that I have blue chains. These are my hydrocarbons, and the red molecules is my water. And the question is, how does this mixture behaves when we put it into a molecular simulation? So I hope that you can see my movie. And what you see is that I start from a complete mixed system, and within very limited amount of time, within a few femtoseconds, the system phase separates. So on the left, where I have the titanium dioxide, the hydrophilic confinement, the hydrophilic wall, as one might expect, if you have two phases, water will go on the wall and hydrocarbon will be in the middle. If I have on the right a silica carbide, which is a hydrophobic, guess what? The hydrocarbon goes and aligns near the wall and the water is in the center. This is a very beautiful two-phase mixture. And of course, we can quantify this phase separation through this density distribution here. You can see the interface and so on and so forth. Beautiful results. Okay, and the question is, again, at every point, my question is, how does this compare to reality? I'm not going to go into details, but we were very happy when some years ago, the group of Professor Gladden, Lynn Gladden is one of the most well-known experimentalists for this kind of systems. She's in Cambridge. She did different kinds of techniques, NMR spectroscopy, pulse field gradient, and essentially she studied the dynamic behavior of this system, of exactly this system. This is also a very interesting project, again, for low temperature Fischer-Tropsch. And what Gladden and her group concluded is that their experimental data were in excellent agreement with the observation from the simulation of water C28 equilibrium for this titanium dioxide pore. And these were our own simulation. Again, so which means that we had an external group validating our results with an excellent agreement. So we moved on further, and we did also coarse grain simulations with the two different walls. Now we have graphene on the left, graphene oxide on the right, and on the very left, I have my all-atom simulations. And as you can see, qualitative, the system behaves exactly the same. And I just want to show this because we can go now, going from all-atom to coarse grain, I can do sizes of pores which are getting closer to reality. So I can do from 5 nanometers opening to something like 17 nanometers opening. So I get close to reality. One other thing that we have done, and I will go very briefly through this, is, as I mentioned before, we have some side products from this reaction, and one of them has to do with oxygenate molecules, dodecanol. So dodecanol, if you think about it, you have a hydrophobic tail and a hydrophilic head, the hydroxyl group. And if you have some basic physical chemistry, what do you expect? A molecule like this will go at the interface. And this is exactly what we have seen from our simulation. The dodecanol goes and aligns at the interface between the aqueous and the hydrocarbon phase. In addition to the qualitative behavior, we also got quantitative data. And the quantitative data has to do with the diffusion coefficient of the different molecules. Mostly here I have, again, not mostly, exclusively, I have hydrocarbon and water. I have many figures, but I will just give you an overview of this. The left two sets of figures refer to all atom representation, graphene and graphene oxide. On the two right is coarse grain, graphene and graphene oxide. And the agreement between the all atoms and the coarse grain representation was excellent. Excellent. In addition, what we found is that a few highlights from these calculations is that, of course, the mobility drops close to the pore surface, which is something expected because you have close interaction between the pore and the fluid. But as you move away and you get close to the center, this is what we call region 2, the simulation is very close to the bulk. So, for example, here we have the hydrocarbon, and we can see here that this is the bulk, this is the discrete and the agreement, sorry, the confined and the agreement is very good. And the other thing is that the presence of dodecanol reduces slightly the water mobility. And this is just the binary mixer, this with the dodecanol. So in general, we were able to get very good quantitative behavior of the system. Now, the complexity increases by adding the nanoparticle, the cobalt nanoparticle. And this has been also a challenge for us. And the reason for this is simply that we didn't have a force field for the cobalt nanoparticle. The question is, how does the cobalt nanoparticle interact with the fluid? And in order to resolve this, we relied on density functional theory. So essentially what we did is we developed some slabs of the cobalt at different configurations. You can see this here, 111 and 100. And we had small clusters of water and butane molecules representing the hydrocarbon. And we did density functional theory for different configurations. Calculations were done in order to reproduce the Martini convention 4:1. So essentially we use butane to represent with one bit in the Martini representation. So what we did is we did density functional theory calculations. I'm not going to go into details for different conformations. You can see this is the energy versus distance for the case of butane close to the cobalt slab, and for the case of the water cluster close to the cobalt. And to this, we passed a molecular model of this kind of functional form for the case of butane and for the water with the cobalt cluster. So in this way, we also developed a force field. And now this is the full system. This is the full system of the cobalt nanoparticle into the fluid. I have now here the wall, the confinement. I have the hydrocarbon, the water, and the cobalt. And the question is, how does the system behave? We did simulations with different compositions of water with hydrocarbon. Very little amount of water means that we're in the beginning of the reactor. As the reaction proceeds, we have a lot of production of water. And you can see that once we reach a high amount of water, anything about 15 to 20%, the water goes and surrounds the cobalt nanoparticle. So you can see this is the mole fraction of water. At around 30%, the cobalt nanoparticle is fully covered by water. And this, of course, has some implications on the diffusion coefficient of the mobility of the cobalt nanoparticle. You can see here the diffusion coefficient as a function of the mole fraction of water. And in the case where we have an excess amount of water, the diffusion coefficient goes up. Here I have two different sizes of cobalt nanoparticle, 2 nanometers and 4 nanometers. These are the most recent simulations for this project. Again, I didn't go into the needs for computational time, but this is really computing intensive. And at the moment, we're trying to reach our limits. And we are looking at cobalt nanoparticles in the order of 10 nanometers. This is something work in progress. Let me talk for another, maybe, I would like 10 more minutes. Marcelo, is that okay?
Sure, Yanis, please go ahead.
So I would like to talk a little bit about a second project that has to do with a different problem. And this problem has to do with the separation of gas mixtures. Those of you that are chemical engineers, you may be aware of the fact that industry spends a lot of energy on separating mixtures, okay? In fact, the majority of the processes in the oil and gas industry involves mixtures. And if you look at some data, maybe 50% of the global energy is consumed by chemical industry for separation processes. One of the most well-known examples have to do with the paraffin-olefin separation. I can think of ethylene ethane, propylene propane, and so on. And these are mostly done by thermal processes. Of course, CO2 is becoming a major issue over the last decade or so. Everybody is looking at ways to control CO2. So essentially, we would like to capture CO2, separate it, and then either sequester it or use it for production of other products. So the question is, what can we do? How can we go from thermal processes to something more energy efficient? And one way to do this is by implementing membrane-based separations. We have different kinds of materials that are used for these kinds of separations. We know classically the zeolite materials. We have mesoporous silicas. For the last maybe 20 years, carbon nanotubes has been used for these kinds of separations. But today I would like to talk more about what we call MOFs. These are solid materials. MOFs stand for metal organic frameworks. So metal is a very critical part of the composition of these MOFs for a number of reasons that will become apparent in a minute. And MOFs are becoming more and more popular for this kind of separations. So before I get into the MOFs, I would just like to give you a very schematic overview on how binary mixes are separated using membrane materials. So we have two different types of separations. These mixes can be either separated based on kinetic or size-based selectivity. So essentially, if you think of a binary mixture of small and large spherical molecules, essentially you have this kind of bottlenecks, if you want, and because of the size selectivity, the smaller molecules will move faster than the larger ones. On the other hand, you may have the case of affinity or some kind of preferential interaction between the membrane material, the wall, and one type of molecules. And this is the so-called adsorption-based selectivity. And you can see here that if the small molecules are adsorbed on the surface of the membrane, then the larger molecules will diffuse faster. The combination of the two, of the diffusivity and the solubility, is the so-called permeability. And if you have a binary mixture of I and J, essentially you can define the so-called perm selectivity, which is the ratio of the two, of the permeability of the faster permeating molecule versus the slowest. So, of course, if you would like to design a process, what would you like to achieve? You would like to maximize your separation factor by maximizing the permeability of the fastest. The problem is that the two things work inversely proportional. So the higher the permeability of the fastest one is, the lower the perm selectivity. So people have been working for decades now, more than 30, 40 years, to design membrane materials that will work for this kind of separations. And what I show here is the diffusivity for various gases in the so-called ZIF-8. ZIF-8 is the zeolitic imidazolate framework. This is probably the most well-studied ZIF. And you can see here that the diffusivity of various gases, and of course, as you expect, this is based on the so-called penetrant size. So this is a kinetic diameter of the molecules. The smallest molecule, as one might expect, diffuses faster than the heavier one. And essentially, this gray zone here defines the so-called the critical zone where molecules can separate, and at the same time, the permeability is appreciable. So everything to the left diffuses very fast. Anything to the right essentially does not diffuse at all. So the question is, how can we modify this active range of separation in order to achieve a particular type of separation? And of course, you can do this in many different ways. We are doing computational work. So essentially, our work focused on looking at the molecular structure. This is my elemental cell of the ZIF. This is the metal, carbons, nitrogen, hydrogen, and so on. So essentially, you can either replace the metal with one with a shorter ionic radius. This essentially will tighten the hinge, or you can replace this hydrogen here with something bulkier. So in this way, the aperture will, the size of the aperture will decrease. And the way that this works is, in reality, is more like, sorry, excuse me about that. It's like a saloon door. I mean, we have all seen movies, Western movies, where you have this door with the hinges, and essentially people, when they try to move through, this open and closes, and it vibrates. And this is exactly the same way things work at the molecular level. I will show you, let me jump forward and show you a movie. Okay, here it is. This is my ZIF-8. These are generated from molecular simulations, and you can see that they have this kind of motion, which essentially they modify the aperture here, and they allow molecules to diffuse through. The way that this is being done, let me go back to my presentation, is using molecular simulation. And this is the only slide with equations, but I had to show you this because I would like to show you the kind of representation that we do. I go back to my earlier argument that we need some quantum mechanics simulations, density functional theory, in order to calculate the force field. And you can see the type of force field that I have. This is the typical Lennard-Jones potential, the repulsive term, the attractive term. The MOF is highly charged. So, excuse me, but I need to turn on my light in my office. Yes, okay. If I don't move, the lights go off. So, and then I have charges here, so which essentially I calculate from density functional theory calculation. This is with the red is what we calculate from quantum mechanics, bond stretching, bond bending, and the torsional potential. And then all these red again are calculated from density functional theory. Once you have the force field, you can reconstruct the structure at the molecular level. We can very accurately calculate the bond angles, the bond length, the aperture, and this can be compared to experimental data. And then, of course, we can proceed with calculating the important thermodynamic properties. And again, the two properties that I mentioned before is solubility. For the solubility, you can do, for example, Widom test particle insertion. You take a molecule of your gas, you throw it into the structure of the MOF, you calculate the interaction potential of this test particle with the environment, and through this you can calculate the excess chemical potential, and the excess chemical potential can give you the solubility, the Henry's law constant, and so on. On the right, we calculate the diffusion, and again here we can either do molecular dynamic simulation, or in the case where you have a fast diffusing molecules, you can do umbrella sampling, transition state theory, and so on. So before I get into some of the results, let me show you the kind of molecular engineering that we did. So we started with this ZIF-8. I forgot to mention that ZIF-8, the basic metal here is zinc, and we go to the left. We substitute cobalt for zinc, and then further we used beryllium. And then also we did a hybrid. So we started with ZIF-8, but we replaced the hydrogen with this bulkier aromatic group. What do we achieve by this? We tighten the bonds, so this is smaller metals, and we make it smaller aperture. So we go from 3.44 down to 3.3 angstrom. So this is very critical in order to achieve diffusion-based separation. I showed you this. Let me jump straight away to some calculations. This is a very, very busy plot. I don't expect that you will be able to follow all of this, but I would just like to show you a couple of examples. What I have here for different classical mixture gas, binary mixture gas separations, I have the selectivity. Selectivity, remember, is the ratio of the permeabilities versus the permeability of the fastest diffusing. So, for example, here I have helium methane. On the y-axis, I have the ratio of permeability of helium versus methane versus the permeability of the helium. With the dashed line is the so-called Robson plot. Robson was a guy that was working for Air Products in the late 1970s, 80s, one of the most well-known industry. And he claimed that for every binary gas mixture, there is a master curve, which essentially shows you the limit that you can achieve with any type of material. Since that period, material science has tried to come up with new structures that will go on that direction. Essentially, for any kind of separation, you would like to be in the top right, maximum selectivity for maximum permeability. And this is what some people, in fact, this is from the group of Bill Kors in Georgia Tech, they call it commercially attractive region. If you are in this region here, in the shaded red, then, and you have a membrane, then you are in business. And what I have here, I have different kinds of structures. These are mostly experimental data. The blue is polymeric materials. The red is MOFs, COFs, mixed matrix membranes, and so on. And then with the green one is predictions from membranes that we design in the computer. So you can see we can start with ZIF-8, which is a standard membrane, ZIF-67, remember this is the cobalt, beryllium, the hybrid, and so on. We have looked at many different kinds of structures, and you can see that in the majority of cases, the new materials that we propose, they're in the so-called attractive region. Let me open here a parenthesis, say this beryllium seems to be the most attractive of all the membranes. We were very happy. The problem was that the whole group that was happy was computational. So when we tried to talk to experimentalists, we figured it out that nobody wants to work with beryllium because it's super toxic. So this is the kind of cases where you have a beautifully designed new material in the computer, but when it goes to reality, it doesn't work. We haven't given up on this. We have new materials that we're working on, but I mentioned this example in order to show you how computational engineering can help you design new materials. One other kind of calculations that we did is to look at adsorption-based selectivity. So essentially what we do here is that in the MOF, we put some new materials, in this case ionic liquids, which essentially work as adsorbent for the gases to be separated. And I do not have a lot of time to go on this, but we look at many, many different ionic liquids. This is just some examples where we're looking at the adsorption selectivity versus the amount of the ionic liquid that we put into the MOF. And you can clearly see here, these are different structures, different colors correspond to different structures, that always there is an optimum amount of ionic liquid that will give you a maximum selectivity. Okay, because I'm running out of time, I will go through this in a very fast mode. Essentially, what we have been doing in the last 2 years on this project has to involve machine learning. And machine learning is something that people are using nowadays for many, many different things. In our case, we use machine learning in order to accelerate the computational work that we do. And I would just like to give you an example. My postdoc and now collaborator, Panagiotis Krokidas, has been working on many years on generating different structures in terms of different linkers, different metals, functional groups, and so on, and looking at different gases to be separated. So he developed a very large database. Now we're getting to 1,000 different simulations by combining 72 different ZIFs and 12 gases. This kind of massive computations took him more than a year in a multi-processor computer that we have at Exinem at Qatar. And the question is, how can we do better? How can we use this data in a systematic way? And the way that Panagiotis did it is that he involved different kinds of machine learning algorithms. And based on this, he developed a methodology that allowed him to predict the diffusivity of penetrance inside ZIFs. I will not go into details, but I would like to show you, this is on the bottom right. This is the predictive diffusion coefficient versus the simulation one. And you can see that we have orders of magnitude difference. We do not claim that we have perfect agreement, but this kind of calculations can be done in minutes compared to months or years to generate the molecular simulation data. What we currently do is we're trying to do the opposite. So essentially, if we have a particular kind of separation that we have in mind, we're asking the computer, we're asking the machine learning tool to design a particular structure for us that will give us this kind of separation. Panagiotis is using genetic algorithms. I will not go into details, but let me show you an example. So we said, okay, we would like to have a material that will give us a diffusion coefficient in the order of 10 to the minus 10 square meters per second, and this kind of separation efficiency, 10,000, 10 to the 4. So what we did is the tool that Panagiotis has designed, the machine learning tool, provided a broad range of answers, different structures that they give this kind of specifications in the order of 4 for the selectivity and in the order of 10 to the minus 10 for the diffusivity. And what he did is he went back and he did simulations, and the simulations gave us indeed predictions that are very close to what the machine learning tool was telling us. So essentially, he went backward from the kind of separation that he wanted to the material that is able to provide this kind of properties. And this is a structure that at the moment, I really do not remember what it is, but it's one of the most that he investigated. Okay, so I would like to come to an end and just conclude by saying that what I call computational molecular engineering is a very powerful design tool for advanced chemical processes and materials. You can use it to optimize processes, reduce energy, design materials with advanced end-use properties, and so on. What is very important in order to be able to get accurate predictions is that you need accurate atomistic and coarse-grained force fields to calculate inter and intramolecular interactions. This takes a lot of time. We rely on quantum mechanics simulations, but recently lots of colleagues have used machine learning techniques to develop this kind of force fields with very, very promising results. Multi-scale modeling that includes physics-based machine learning models can also accelerate the simulation of complex systems. For example, when you have multi-phase, when you have interfaces, and so on and so forth. And of course, in this kind of effort, we should not forget experiments. Comparing to experimental data at different scales, molecular, macroscopic, is also very, very important in order to be able to validate our model predictions. This is my team. I have been working many years for all of these people. I provided, essentially, I spoke about 2 different types of projects. The Fischer-Tropsch synthesis. This is a project that started when I was in Demokritos. Professor Castier mentioned this. Currently, Asma Marzouk is the person in charge of the project. And then on the ZIF design, I work with a number of excellent collaborators here in Texamat, Qatar. Professor Ed Brothers was the head of the quantum mechanics group that developed the force fields. Professor Castier and myself were in charge of the simulations and macroscopic calculations for the design of ZIFs. Haikon Jong is a long-term collaborator from College Station doing experimental data to validate our simulations. And at the moment, Amro Mohammed, he was a master student of mine some years ago. Now he's my postdoc that has taken over the project. And hopefully soon we will have some very exciting results to share with you. And on the right, I have the funding that we got over the years from different sources. I would like to point out that Texas Instruments Qatar has a very powerful high-performance computer. We have been very fortunate to run heavy-duty simulations for many years and get some of the excellent results that I showed you today. And with this, I would like to thank everyone, especially Christian and Marcelo, for giving me the opportunity to be here today and share this data and these calculations with you. And I will be happy to answer any questions that you may have. Thank you very much.
Thank you very much, Yanis, for this beautiful presentation. We got some questions, and I see that people are commenting here on YouTube. Also, thank you for the presentation. Well, I will be kind of selfish, and I will begin with a question of my own. But I think it's a question that might be of interest to those in the audience that are not specialists in molecular simulations. And the question I have is the following: what is the barrier to entering this field? Of course, it's to understand the methods, to have to understand thermodynamics. But if I do that, and let's say I have a good computer, now what software is available? What's the role of someone who is doing the modeling? Is like writing programs or applying programs that already exist? So how do you go about entering this field?
Beautiful, beautiful, Marcelo. Thank you very much. Okay. So since I have been in this field for many years now, I would say 20 years ago, the majority of effort was spent on writing code. You know, you could write Fortran code, and we're spending a lot of time in optimizing codes and so on. Nowadays, there is a lot of code available, and there is a lot of code at different level. There is a lot of open source code, but also there is more like advanced code, which gets with a little bit of a price and some, but it has a lot of support. You have graphical user interfaces and so on. Nevertheless, it is extremely important that in order to do meaningful research, people need to have some kind of basic understanding of programming at different levels. I mean, we can name it Python, C++, any kind of programming capabilities, because at the end of the day, if you do heavy-duty calculations, you have to develop your own tools. For example, you can run molecular dynamic simulations using, for example, LAMMPS or GROMACS, which are some of the most popular simulation engines. However, you need to do what we call post-processing of your data. You may want to calculate how systems properties for which you need to investigate local structure and so on and so forth. So always some kind of basic programming skills are needed. Physics is very important. You need to understand, statistical mechanics, because you need to understand the kind of calculations, the kind of limitations that these calculations have. So I would say that someone, of course, as you said, thermodynamics knowledge is very, very important, is the minimum, but then some programming is always very much needed. I mean, I have never been involved in a project where we will go from the beginning to the end with ready-made codes. Always there is a need for post-processing and developing your own tools for this kind of calculations.
Okay, Yanis, thank you very much. We have a question here from Dr. Ahmed Omram from LCS in France, and he says the following: MOFs are not stable, especially in the presence of water. How long ZIF-8 can stand water, and is it cost-effective when compared to zeolite or gas hydrates? What about other MOFs?
Good, excellent. I agree. Yeah, some of the MOFs of the ZIF, many of these ZIFs are not stable in water. And we had this kind of conversation with many of the colleagues. I cannot get into the numbers. You know, I'm not able to give you immediate numbers. I can only mention that ZIFs and MOFs, you know, are more advantageous compared to thermal properties. Compared to zeolites, the thing with MOFs is that you can get more tailor-made aperture. So my understanding is that with zeolites, the tunability is less powerful than what it is with MOFs. You're muted, yeah.
Sorry for that. You mentioned progress on the use of artificial intelligence towards the end of the presentation, but we got two questions from Professor Christian Scherer during the presentation. I'll kind of try to lump them together. One is, what do you think will be the role of physically informed neural networks in molecular simulation? And the other one is, how do you think that data science can improve or accelerate simulations? And I think you gave good examples. For example, for parameter fitting, preliminary classifications of data.
Yeah, that's very good. So, as I mentioned, there is a lot of effort. In fact, last week we had a conference in Spain on physical properties and phase equilibria. This is a conference that goes on every 3 years. This is the most, I would say, prestigious conference in our field. And there is a lot of work on developing force fields based on machine learning tools. I can tell you in particular, one very, very difficult problem to come up with is a force field for water. And Professor Panagiotopoulos from Princeton, who is one of the leaders in our field, he showed some recent work on using machine learning and artificial intelligence to develop new and effective force fields for water. So, and this combines machine learning with quantum mechanics. So I think there is a great opportunity in that field. The other question about physics-based artificial intelligence, yes, I think it's also a powerful way to move forward. I mean, as you put physics into your data manipulation, it helps tremendously in moving forward with designing new materials, new processes, and so on.
Okay, thanks again. We have a question from Dr. Fatma Jubeiro, and thanks, Fatma. And her question is, what do you suggest about the type of membranes for studying thermodynamic balance between pharmacophore molecules and protein targets?
I'm not an expert in this area, so I'm not gonna, I don't think I have an answer to this.
Okay, right. Yeah, then I have some comments here from a person called Tada, thank you. He says, I think there is always a compromise between computation time and the quality of the simulation, the loss of information. Do you think or know some case where is some kind of important information that current popular machine learning techniques cannot handle or predict successfully? So if I understood the question correctly, the question is, so if you do, say, artificial intelligence, do you miss something that molecular simulations could do, or perhaps the other way around?
Okay. I'm not going to answer exactly this because I cannot provide specific details, but I can say this is in the heart of our work. Always, as you go to more coarse grain or you go to simpler force field, you are missing some details in the intermolecular interactions that affect the end results. I can give you a couple of examples. One has to do again with water, and a particular example is water with hydrocarbon. These kind of systems, they have experimentally two phases, liquid-liquid equilibria. In order to be able to predict this kind of behavior over a broad range of temperature, you need more than two body interaction potentials. The majority of calculations that I showed you today is based on two body interactions. So essentially, you assume that all the interaction can be calculated based on pair-pair interaction. This is not the reality for the case of water. Polarizability effects are very, very important. The problem is that when you introduce the many body interactions, the computational time increases. Of course, you gain some accuracy in the calculations. I mentioned water with hydrocarbon, but in general, always there is the fine balance. How detailed you can go into the calculations, but at what cost? You can translate this into machine learning and artificial intelligence. I do not have a specific example to give you, but for the case of AQ systems that I mentioned, this has a tremendous effect and still is an open problem.
Thanks, Yanis. We have a question from Mr. Dr. Gustavo Espinola Mena. First, he thanks you for the presentation. And his question is, can these studied structures, I think that he mentions, he refers to the ZIFs, be useful to carbon capture technologies, CO2 capture technologies?
Yes, this is true. Yes, this is the case. For example, we have shown in one of the examples that I showed you, we had CO2 with methane, CO2 nitrogen. Yes, some of this structure can be used for CO2 capture. Of course, this is in principle that can be used. This is kind of technology in its infancy. You know, the amount of CO2 that we need to capture is massive. So there is a significant scale up. Personally, I'm not in the business of scaling up, but in principle, yes, CO2 can be captured from mixers by using this kind of technologies.
We have first a comment and then a question from Mr. Gustavo M. And first of all, he was fascinated by the subject of ZIFs during your presentation. And then his question is, what does a chemical engineering undergraduate student need to do work or study ZIFs? How can he prepare himself to go to the level of the presentation, level of work you presented?
I think this is a very nice question. I always believe that if someone wants to work on this at the undergraduate level, a course in physical chemistry with a basic course in material science will help getting some basic understanding of this kind of materials and this kind of behavior. So physical chemistry and material science will give you a very good background.
Then there is one more question here, but I have to read it before. So I make one of my own, which is the following. Yanis, of all the applications of molecular simulations, what are the fields or applications that you think are the closest to industrial practice currently?
Oh, we have a lot of cases where this kind of molecular simulation is used in industrial practice. So, I mean, I have lots of former PhD students and master students and postdoc who work today in industry, and they work on all kinds of problems. For example, I can tell you immediately the hydrocarbon industry, they are using molecular simulation to predict properties. I didn't touch at all, for example, the pharmaceutical applications. Pharmaceutical industry is using molecular simulation. The chemical industry, they are using molecular simulation to predict properties. So there is a lot of work going on in industry. The thing is that one of the things about molecular simulation is that calculations always take time. And I keep saying this. For example, Marcelo, you and I were chemical engineers. So for example, for the chemical engineering in the audience, running Aspen and predict some properties, you know, it's like at within seconds. But predicting properties using molecular simulation needs significant computational time. So I didn't get specific, but there are many different applications in pharmaceutical, in oil and gas, in chemical industry, materials design. But you need to invest. You need to invest in computing time and resources.
Okay, now I have a question from Professor Paula de Barros Barreto from the German Paraguay University. She's teaching a thermal class and she took a break in the class. Well, not a break, actually took time of her class, so all her students are watching you now. And her question has to do with the following: how can you validate the results of molecular simulations if the materials you are studying have not been synthesized yet?
Very good point. You can validate at different stages. So you can even either compare to a similar material using changing somehow the chemical structure, or you may have experimental data for the material at different conditions. If it is a complete new material, Of course, you only have to go and synthesize it and measure the properties. You have no other ways. But the way you do the validation, the comparison, we usually do it gradually. So we start from something that looks similar and for which we have data, and then we increase the complexity.
Well, I think this was the last question we had. Thank you very much, Yanis, once more. I would like to thank the audience for being with us, for sending these comments and questions. I think the question answer part of the session was very lively, very interesting, very rich. So I don't know whether Christian would like to say a few words to close the session.
Yeah, I would like to thank Professor Ioannis Economou. I would like to thank Marcelo Castier for being the chairman as well. And I think that I would say this is our first talk, and in an historical moment, I really emphasize that in order that we have our first talk with a colleague from Qatar, from Texas as well. So I'm very happy, and I hope that we can maintain this. And this is going to be, I hope, the first step for initial long cooperation, something like we can discover in this moment. Thank you very much for all the audience, and be in touch.
Thank you. Thank you again.
Thank you.
Okay, bye-bye.
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 Excelente, Marcelo. Opa, no se escucho. Está muteado.
Todavía estamos en vivo, ¿no?
No, ya salimos. Sacarnos el vivo.